Welcome to section 8.1. In the video before this, we reviewed quite a bit about matrices. We ended with Gaussian and Gauss-Jordan elimination, which we used to find eigenvalues and eigenvectors. In that video, I told us the reason that we were finding the eigenvalues and eigenvectors is that eventually we would be looking at a system of differential equations, and we would need those eigenvalues and eigenvectors to solve the system. And so that's what we're going to be taking a look at today. We are going to start by just writing the system of linear or ordinary differential equations in matrix form. So let's jump right in. Let's consider this system that we have right here, which has linear first order differential equations. So we're going to notice all of our coefficients are functions of t. We have x1, x2, all the way to we have some function of t at the end. That can be written in matrix form as the following. We are taking the derivative of the column matrix x1, x2, all the way to xn. And we're going to have a coefficient matrix. So we have a11 of t, we have a12 of t, so on and so forth, all the way to a1n of t. And this goes all the way down to an1 of t, an2 of t, all the way to ann of t. And those are the coefficients on x1, x2, all the way down to xn. So far, when we multiply these two, we get this part of the equation, and this part of the equation, and everything in between, obviously. And then we are going to have to add those end functions, the f1 of t, f2 of t, all the way down to fn of t. Now, writing this a little bit more efficiently, this matrix, our coefficient matrix, we write that as a of t. We write this column matrix as x, and we write this column matrix as f of t. So another way to write this is dx dt is equal to at of x add f of t, or it's sometimes written as x prime is equal to ax add f. And in this case, you just need to make sure that you recognize that a is a function of t and f is a function of t. We're also going to be looking at cases where we have a homogeneous system, in which case we would get dx dt is equal to a of t times x. This video is going to cover the background of these linear systems. So we're going to use matrices to write our linear systems, and then we're going to be looking at the superposition principle and homogeneous versus non-homogeneous systems. So we're not actually going to do any of the solving in this video. This is just all the preliminary or the background theory, and then in the next video we will actually be solving. So let's take a look at our first example. First thing that we want to do is be able to write a system in matrix form. And so here is our example. So this dx dt is our x. Our coefficients will be our a of t, and then those functions at the end are our f of t. Okay, so we get our x then is just x and y. Our a of t is the coefficients, so the -2, 5, 4, and -3. And our f of t is that e to the t, subtract 2t, and the 10t. So our system then can be written as dx dt. Now it's a little hard from my writing. This x is capital, so the capital X denotes that it's a matrix. So we get dx dt is equal to -2, 5, 4, -3 times our matrix x, add that f of t. And then we're always going to clarify what that matrix x is. Alternately, this can also be written as x prime is equal to -2, 5, 4, -3 times x. And we might choose to split this up So we have 1, 0 times e to the t, and then we have -2 and 10 multiplied by t. So that is the first step for today, is writing our system in matrix form. Let's move on. Next thing that we want to talk about is a solution vector. So a solution vector on an interval I is any column matrix X, and it's going to look like this, x1 of t all the way down to xn of t, whose entries are differentiable functions satisfying the differential equation. So let's take a look at an example. In example 2, we are verifying that x1 and x2 are in fact solutions of this given equation. So looking at the equation, of course, we're going to need x prime, and then we're going to need to plug it in. So we're going to do that twice, once for each matrix. I'm going to start with just that first solution one. So if I take x1 and I take the derivative of it, that's going to give me -2e to the -2t, and then 2e to the -2t. And so now I'm going to substitute in my x prime and my solution into our equation and see if I end up with something that's true. So I have -2e to the -2t and 2e to the -2t, and I want to know, is that equal to my 1, 3, 5, 3 multiplied by x? So if I actually multiply on that right side, remember we're going to do row times column, so I would get e to the -2t, subtract 3e to the -2t, and then I would get 5e to the -2t, subtract 3e to the -2t. And so finally then, we get -2e to the -2t, 2e to the -2t, does in fact equal the right side of the equation, but I'm too lazy to write it. So we have proven that x1 at least is a solution of the equation. Now we got to do the same thing for x2. So for x2, I'm going to take the derivative, and when I do, I get 18e to the 6t and 30e to the 6t. Substituting into the equation above, I get 18e to the 6t, 30e to the 6t. I want to know if that's equal to my 1, 3, 5, 3 multiplied by my solution vector. So right side of the equation, that gives me 3e to the 6t, subtract 15e to the 6t, sorry, adding, and then I get 15e to the 6t, add 15e to the 6t, which is in fact true. So we have just verified that both x1 and x2 are solutions of that system of differential equations, so this equation right here. Okay, so let's move on and talk about some more preliminary theory. Next thing we're going to talk about is initial value problems. So we are going to let t be an element of some interval I, and when we substitute that t naught into x, we get some column matrix x1 of t all the way to xn of t. And we have x naught is some column matrix of constants. So lambda 1, lambda 2, all the way to lambda n. Then the initial value problem is solve some equation subject to the initial condition. So that shouldn't be shocking. That is very similar to the initial value problems that we've seen before, just written in matrix form. Now, what we've often cared about before is, does a solution exist to the differential equation, and is it unique? And so that's what we're gonna talk about next. Let entries a of t and f of t, so from the equation above, be continuous on some interval I that contains t naught. So they have to be continuous and they have to contain t naught. Then there exists a unique solution of the initial value problem on I. What we're going to move on to next is homogeneous systems. And specifically, we're going to take a look at the superposition principle. So superposition principle says, let x1, x2, all the way up to xk be a set of solution vectors of the equation x prime is equal to a times x, so that is a homogeneous system. Then x is equal to c1 x1 add all the way up to ck xk is also a solution. So that should not be shocking. We've seen that before. What's new is that we are applying the superposition principle to homogeneous systems also. So if you remember, the reason we use the superposition principle is we hope to be able to find some linearly independent solutions to use to form the general solution. So that's a little bit of a preview of what we're going to be getting to. So if we look back to that example that we just did, we had x1 and x2, and they were both solutions of our equation. So then, by superposition, x, which is c1 x1, add c2 x2, is also a solution. So what that tells us is that a constant multiple of a solution is also a solution to the initial value problem. Okay, so where that leads us to then, like I gave us the preview, is linear independence and dependence. Let x1 to xk be a set of solution vectors of this homogeneous equation. Then x1 to xk are linearly dependent if that symbol means there exists. So if there exist these constants c1 to ck that are not all 0, such that c1 x1 add all the way to ck xk equals 0 for every t in our interval. If not, then we say that those solution vectors are linearly independent. Okay, so let's take a look at this example 3. x1 is that 3, 1 times e to the t, and x2 is that 1, 1, e to the negative t, and we know that they are solutions of this differential equation. I want to know if these solutions are linearly independent or dependent. So if they are linearly dependent, then there exists c1 and c2 such that c1 x1 add c2 x2 is equal to 0. Okay, so if we write this in a little bit of a kinder format, that's going to be c1 times 3 e to the t add c2 multiplied by e to the negative t, and we want to know, are we going to get 0, 0? So is there a c1 and a c2 that would make this equation true? Okay, well, solving, what we're going to do is we're going to look at the first coordinates, or first components, and we're going to look at the second components. And so what that gives us then is 3c1 e to the t add c2 e to the negative t equals 0. So that's in yellow. And then the components in green give us c1 e to the t add c2 e to the negative t. And so this is the system that we have to solve. So if I take equation 1 and I subtract equation 2, that's going to give me 2c1 e to the t equals 0. So c1 is 0. And then if I take equation 1 and I subtract 3 times equation 2, that will give me negative 2 c2 e to the t equals 0. So c2 equals 0. So because c1 and c2 are 0, what that tells us is that x1 and x2 are linearly independent. Now, of course, that wasn't very efficient. So if we've done, when we did linear independence and dependence before, how did we show that solutions were linearly independent or dependent? Well, what we looked at was the Wronskian. So that's what we're going to take a look at next. Okay, so let's consider that we have solutions vectors x1, which is x of 1, 1, all the way to x of n1. And we have a bunch more solution vectors all the way up to x of k, which is x of 1k, all the way to x of kk. Now, for those solution vectors x of 1 to x of k to be linearly independent, we say it is both necessary and sufficient, so it's both necessary and solution, for the Wronskian of x1 to xk, which is the determinant of the matrix x of 1, 1, all the way to x of 1k. So I used the incorrect notation above. That should be a k. And then we're going down to x of k1, all the way to x of kk. That Wronskian should not be 0 for all t in our interval. Okay, so that's a big difference for all t that are in the interval. So when we've done this before, there just had to exist some t. Well, now it's not some t, but it's all t in the interval. So let's take a look at an example. So here we go. Let's take a look at that same example that we already did. We already know that x1 and x2 are linearly independent. Now, the way that we would show that if we used the Wronskian, so the Wronskian of x1 and x2, we're going to find the determinant of the matrix. First solution is 3e to the t, and then we have e to the t. Second solution is e to the negative t and e to the negative t. So if we found the determinant, we would have 3 subtract 1, which is 2. Because that determinant does not equal 0 on the entire interval of negative infinity to infinity, that tells us that x1 and x2 are linearly independent. Okay, so thinking back to why do we care if the solutions are linearly independent? Well, if we have solutions that are linearly independent, we can form a fundamental set, and the fundamental set then helps us form the general solution. So of course, that's what we're going to look at next. Next thing we want to talk about, general solution. So let x1 to xn be a fundamental set. So a fundamental set means that the solutions are linearly independent. Then the general solution is x is equal to c1 x1, add all the way up to cn xn. Sorry that my notation switches a little bit. Sometimes I used n, sometimes I use k. Hopefully it doesn't matter to you. So returning back to that example that we just did, we've shown in 2 ways that x1 and x2 are linearly independent solutions of this homogeneous system. Because x1 and x2 are linearly independent, the general solution then is x is equal to c1 times x1, which is that 3, 1 e to the t, add c2, 1, 1 e to the negative t. So what we're going to end the video with, similar to when we've done this before, is non-homogeneous systems. So now we have linearly independent and dependent. We have the Wronskian for homogeneous systems. How does this translate to a non-homogeneous system? Well, first let's talk about the solution. So let x1 to xn be a set of solution vectors of the homogeneous system. We also then have a particular solution, which is a solution vector of the non-homogeneous system. By superposition then, x, which is c1 x1, all the way up to cn xn, add xp is also a solution. This part right here, we've called xc, the complementary solution. So that's just the C1, X1, all the way up to Cn, Xn. So if that is a general solution to the homogeneous system, then that X, which is X of C add X of P, is the general solution to the non-homogeneous system. So this should be similar to when we did non-homogeneous linear equations. If you remember, we found the complementary solution, and the complementary solution was the solution to the homogeneous system. Then we had to find the particular solution. It's the same thing when we're looking at systems rather than just equations. So let's take a look at our last example. So we are given this equation right here, and we have this particular solution. First thing that we're going to do is we are going to verify that that particular solution is in fact a solution of the differential equation. So first thing that I'm going to do is I'm going to substitute this in to my equation right here. So I have x prime is equal to ax add f. So my x prime is going to be 3, -5, and I want to know, is that going to be equal to 1, 3, 5, 3 multiplied by 3t subtract 4, -5t plus 6, and I'm going to add that to 12t subtract 11 and -3. So I'm going to do everything on the right side, left side can just stay the same. So if I multiply here, I'm going to get 3t subtract 4, subtract 15t, add 18, and then I'm going to get 15t subtract 20, subtract 15t, add 18, and I'm adding to that the 12t subtract 11 and -3. So that first matrix simplifies to -12t, add 14, and -2. And I'm going to add that to the 12t subtract 11 and -3. So ultimately, I get 3, -5, which is in fact equal to 3, -5. So what we've proven, or verified, is that xp is a solution to the equation above. So then our general solution is going to be of the form complementary solution add particular solution. Okay, complementary solution comes to us from example number 2. So in example number 2, we were given our two solutions. Solution 1 was 1, -1 e to the -2t. Second solution was 3, 5 e to the 6t. And these are linearly independent. You can prove it if you want to, or you can just trust that it is. But in our second solution, we looked at, or our second example, we looked at just this system right here. We looked at the homogeneous system. So homogeneous system gave us these two solutions. Then once we've now looked at our non-homogeneous system and gotten our particular solution, where that leads us to finally is that the general solution to this non-homogeneous system is going to be x equals c1 times 1, -1 e to the -2t, add c2 times 3, 5 e to the 6t, and finally add our particular solution. So that 3t subtract 4 and -5t plus 6. So that is our general solution. Okay, thank you for sticking with me through this video. In this video, we looked at the preliminary theory to solving systems of ordinary linear differential equations. We differentiated between homogeneous systems and non-homogeneous systems. We looked at the Wronskian. We reviewed the fundamental set. So where this is leading us to, in the next video, we will actually be solving the homogeneous systems. So until next time, thanks for watching.